Today we want to start our last unit of the year. The unit is called Simple Harmonic Motion and Waves. Now, all of you have some intuitive notion as to what a wave is. We talk about, or we see water waves, right? The water waves as they come in towards the shore of the beach, or at the wave pool, where the water waves are produced down at the end of the pool, and they come on up to the other end, where the beach is in the wave pool. We've seen waves in other places as well, right? Sometimes I put up my Christmas lights a couple of weeks ago. When I put up my Christmas lights, you got extension cords, right? And sometimes you give the extension cord a flick to get it over something or around something. And you see this wave traveling through this extension cord. We all have some notion as to what a wave is. We don't necessarily have a notion as to what simple harmonic motion is. This is what we're going to cover today. And on the surface, it's going to seem not related to your notion of waves. Bear with me for a few days. In a few days, we'll draw the connection between these two parts of the unit, simple harmonic motion and waves. There is a clear connection, but I can't tell you what that clear connection is yet until I've explained what simple harmonic motion is. So, that's what we're going to do today and over the next few days. I'm going to define simple harmonic motion for you right now. When you write down this definition, you see it and you write it down, it probably won't make any more sense to you than simple harmonic motion does right now. The definition, without being explained, is ambiguous at best, but I will explain it. Simple harmonic motion is motion toward a fixed point, whatever that means, with a force, and therefore acceleration, that is proportional to the displacement. So you read that, you write that, you probably don't know anything more, or you probably don't have any better understanding, I should say, of simple harmonic motion than you did 5 minutes. What do I mean by that? What do I mean by motion toward a fixed point with a force that is proportional to the displacement? Take a look at the diagram that I see here, guys, that you see up on the board here now, guys. This is going to be kind of a wall or some fixed, some point where the spring is attached. So we're attached to this wall. And then the other end is free to move. But this red line is going to represent our fixed point. So that's where the end of the spring is if it's not stretched or squished. That's just, you got a spring sitting on a desk, that's where the end of it is. This is our fixed point. Remember we defined simple harmonic motion as motion toward a fixed point. So that's going to be an important spot, okay? Motion toward that fixed point right there where the force is related to the displacement. All right. Now bear with me on this, okay? This is a spring that is not stretched or compressed right now. But I can stretch it, I can compress it. I'm going to stretch it right now. I'm going to stretch it just a little bit. There we go. Stretch just a little bit right there. Because it's stretched a little bit, the displacement is just a little bit. There is a force that pulls this spring back to where it came from, towards that fixed point. We call that a restoring force. And you guys have all experienced that, right? If you stretch an elastic or a spring, you feel it pulling back, right? You feel it pulling back to where it came from. Here's the thing though, if I stretch it more, it's further out, the displacement is bigger. I don't mean displacement delta D. Like displacement delta D would be, if I picked the spring up and threw it across the room, that would be a delta D displacement. Okay, I mean the displacement, how much it's stretched. If I stretch it more, you know intuitively that this spring pulls back harder. The more you stretch a spring, the harder it is to pull it. So therefore, the more it pulls back. Let's stretch it a little bit more. Stretch it a little bit more. Okay, now the displacement is even bigger. Guess what? The force that pulls this spring back to the restoring force is even bigger. Bigger displacement, bigger force pulling it back to that fixed point. Sometimes we call that fixed point the equilibrium position. Now, if I was to let this go, what would happen? This is a big force right now. A big force pulling it back to that fixed point. If I was to let it go, it starts going back to that fixed point because there's a force pulling it back to the fixed point, right, Xander? There's a force pulling it back towards that fixed point. That force decreases, but it's still a force. So as there's a force pulling it back towards the fixed point, it speeds up. Look, this is what happens. Big force, smaller force, smaller force, smaller force, smaller force, but big force speeds up, speeds up, speeds up, speeds up, speeds up. That makes sense? You can see here that there is motion toward that fixed point, and the force that pulls it toward that fixed point is related to the displacement. That's different than anything we've ever done before. Everything we've done before involving forces has involved a force that hasn't changed. We might have had 2 or 3 or 4 forces acting on an object, but each one of those forces remained the same for the entire question. Now the force is changing, depending upon where that spring is. Big force, small speed, smaller force, smaller force, smaller force, but as it gets closer to that equilibrium position, the speed increases because that force continues to pull it towards that fixed point, that equilibrium position. Now, what happens right here? Well, right here, the force is 0. There's no force pulling it back to the fixed point because it's at the fixed point. The spring isn't stretched or it's not compressed. So there is no force, but it's now moving pretty fast because it's sped up this whole time as it went from here to here to here to here. Because it's moving fast, it keeps going. Now it starts squishing, but it slows down because there's a force acting this way now. The force was acting this way toward the fixed point. Now the force is acting back this way towards the fixed point. And as this squishes more, that force pulling it back towards the fixed point, this is driving me crazy. There we are. That force that pushes it back towards the fixed point gets bigger and bigger and bigger. So now it slows down, slows down. Eventually that force becomes big enough and it stops. And then the force pushes it back toward the equilibrium position, speeds up, reaches a peak speed. Now the force pushes it back towards the equilibrium position the other way, slows down, stops. Speeds up, slows down, speeds up, slows down, and so on. This is simple harmonic motion. Motion that repeats itself. Why does it repeat itself? Because it is motion toward a fixed point, right? This point right here, with a force toward that fixed point that is proportional to its displacement. The bigger the displacement, the bigger it's stretched or compressed, the bigger the force pushing it back to that fixed point or to that equilibrium position. Another example of simple harmonic motion, I'll take my keys here. Let the keys on the end of this lanyard swing back and forth. That's motion that repeats itself, right? Guess what? That's also simple harmonic motion. It's a little bit more difficult to see why the force is proportional to the displacement, but it is, and that's why these keys go back and forth like this. They swing back and forth in repetitive motion because the force that pushes it to its fixed position, that's this position right here, is proportional to its displacement. Question?
It will eventually reach the equilibrium point again.
Okay, that's a good question. So the question is, if I understand it correctly, is this will eventually die out and end up going back to the equilibrium position? Yes, but in a perfect world, it wouldn't. You guys learned in Science 10 about something called the Second Raw Thermodynamics, and it says basically anytime you have an energy conversion, you always lose a little bit of energy in the process. So we have right out here, we have all potential energy, spring potential energy we call it, and that gets converted to kinetic energy, gets converted back to potential energy, to kinetic energy, to potential energy, and so on. Every time it converts a little bit, we lose a little bit of energy. So it never goes out quite as far as it was. This is driving me crazy. There we are. It never goes out quite as far as it started at. So it ends up doing this. Make sense? If there wasn't a loss of energy, then it would keep going out the same distance each time. But that's impossible because unless it's what we call a forced oscillation, like a swing set. Okay? A swing set, you swing on it, you go back and forth, it eventually dies out, right? Unless there's somebody behind you pushing that swing set, right? If you have a forced oscillation, forced simple harmonic motion, then you can continue going the same height or maybe even higher, right? But in the absence of that, yes, it will eventually die. We call that damped oscillation when there's an energy drain from it versus forced oscillation when there's energy input to it by pushing it or by whatever. Yep.
Can you give an example when the force is generated by gravity? How is the force greater or the greater?
Well, the force of gravity, that's a good question. When we talk about that pendulum, okay, back to that pendulum example of simple harmonic motion, the force of gravity is what pulls it, right? But remember, the force of gravity isn't changing. So how is the force greater depending upon its position? Well, remember we defined simple harmonic motion as the force toward the fixed position. The force toward the fixed position. So if we look at these keys right here, there's a component of a force that pulls it back to here. But right here, it's a different component of the force that pulls it back right here. If you think about it, like these are going to head pretty much straight down right now, right? So gravity, all of that force of gravity is pulling it back to its fixed position. Whereas right here, okay, it's not going to go straight down when I drop it. So gravity is only partially pulling it back to that fixed position. Gravity is pulling it straight down, but it wants to go this way. So there's only a component of gravity that's acting to pull it back. So all of gravity here acts to pull it back, but only part of gravity here, and even less of it here. So the more displacement we have there, the more force of gravity is pulling it back to its fixed position. Does that make sense?
Okay, so in that example,
Yep.
So if we're saying move towards a fixed point, and the example is circular motion, it's along the outside of the circle. So you're drawing that line?
Yes. Yeah, it would.
And otherwise it would just be a straight.
So you're talking vertical circular motion?
Yes.
Okay. So that's a tricky one. You wouldn't consider a vertical circular motion to be simple harmonic motion because as you go around the circle, that gravity, of course, it's always acting down, but it's not always the force that's pulling it back to its initial position, to that fixed position. The component of gravity isn't always proportional to that displacement when it goes past that certain point up there. So basically, when it goes up here, the component of gravity is bigger, pulling it back. But as it go past that point right here, all bets are off there. So we wouldn't consider that to be simple.
It's more just referring to the fact that the pendulum is a circular.
Yep. Yeah, but once you get past a certain point, that analysis kind of falls apart. Of the simple harmonic motion nature of it, that is. Okay. It's about, I think they say the simple harmonic motion nature of it, I think it's about 40 or 45 degrees where it starts becoming a little suspect, not really simple harmonic motion at that point. Okay. All right, so does this kind of make sense, guys? All right, let's take a look at an equation that describes this simple harmonic motion. Nice, easy equation. Really, it's just the definition of simple harmonic motion. We said simple harmonic motion is motion in which the restoring force, the force that pulls it back to its fixed position, is related to its displacement. So let's come up with an equation that says the restoring force, the force that pulls it back to its fixed position, is equal to something times the displacement. F is the restoring force. X, by the way, will be the displacement. Now, didn't we call displacement delta V before? Yeah, we did. We did. If I was to take a spring and stretch it, how much it stretched would be x displacement. But if I was to take a spring and throw it across the room, the displacement of the spring across the room would be the delta d displacement. We're not talking about that. We're not talking about how far the spring moved. We're talking about how far the spring was stretched or squished. So x is that displacement, the amount that it's stretched or squished. K is something that we call the spring constant. And the units for the spring constant would be newtons per meter. And that's basically just a measure of how stiff the spring is. If you take the spring out of a pen, you've all done it, right? Take apart a pen, you take the spring out of a pen, you squish it or you stretch it. It's a pretty loose spring. It's pretty easy to stretch, pretty easy to compress. Okay? The spring constant of that would be small, like 10 or 20 newtons per meter. But if you take the spring out of a car, right, that goes around the shocks of the car, kind of holds the car up. Like that's way, way, way stiffer, right? And the spring constant of that, I'm not even sure what it would be, but it would be in the thousands of newtons per meter because it's stiffer. So K is a measurement essentially of how stiff the spring is. The higher the spring constant, the stiffer it is. So the restoring force, the force that pulls this spring back, this green force that I have labeled here, this restoring force is equal to the spring constant, the stiffness of the spring, times the displacement, how much it's stretched or how much it's compressed. So because it's related to how much it's stretched or compressed, the force here is bigger than the force here, which is bigger than the force here. The force decreases as x decreases, and then the force pulling it back to the fixed position increases as x increases. And then so on and so on. That's what causes what we perceive as simple harmonic motion, which is motion that repeats itself. Now, this is Fr, the restoring force, the force that pulls it back to that fixed position. There's another equation that we sometimes use, Fa, the applied force. How much force did I have to pull on the spring or push on the spring to stretch it or compress it? It's going to be equal to positive Kx, which might make sense. How hard do I have to pull the spring? Well, however hard it's pulling back. If I pull it 20 newtons this way, it's going to be pulling back toward the fixed position with 20 newtons the other way. The difference between these two forces, sometimes people get mixed up a little bit. I'm going to be honest with you. We're not going to lose sleep over which one you use. If you use the first one when you're supposed to use the second one, all that's going to happen is you're going to get a negative number. So we're not going to lose sleep over that. You get a negative number when you should have got a positive. Oh well. Okay, we're not going to take off a mark for that. Now, this is the only version that appears on your data sheet. Sometimes, technically, we're supposed to use the other version if we're pulling on the spring. But again, if you use the first version, it's not a big deal. Now, there is one more equation. Not for force, though. Not for restoring force. A little trickier. This one is not, this one that you see up here is the definition of simple harmonic motion, right? F is related to x. F is bigger as the displacement is bigger. This one refers to the period and the frequency of spring oscillation. Oscillation just means back and forth. The period, the time for one cycle, and it starts here, comes back to that same spot. The time for one cycle is equal to, who are my math 20 people here? Done trig in math? Unfortunately, yes, he says. You don't need to copy this part down. I was to plot a graph of speed versus time. I was to plot a graph of speed versus time of the spring oscillating. Back and forth, right? The spring's going back and forth, back and forth, back and forth. When it's stretched all the way, the spring has a speed of 0. But as it starts moving, the speed increases. And then it goes through the equilibrium, through the fixed position. It's at max speed. And then the speed decreases. And then it reaches the other side and stops. And then it increases going the other way. Goes through the fixed position, decreases, and zero speed, stops, and so on and so on and so on. That's a sine wave, right? That's a sine wave. A little bit of a relationship between simple harmonic motional waves. A little bit. But the point that I want to make with this, and if you don't take Math 20, don't even worry about this. We will not derive this equation. But those of you who are familiar with trig, sine waves, cosine waves, might see a little bit of a connection with this equation for the period of this vibrating spring. The period is 2 pi. Where the heck would that ever come from? It comes from a sine wave. Square root m over k. Now, like I said, I'm not going to derive that whole equation for you, but for those of you who take Math 20, you might see a little hint of a connection. Sorry? Well, except we're not going to use them. So what is, obviously 2 pi is just a number, right? Pi is 3.1415. How many decimal places can you go? 3.14159265. Oh, that's better than me. Yeah. Good. Georgia just made that up, eh? No, she was pretty confident. So she either knows to that many decimal places, which good for you if you do, and if she doesn't, she was active confidence, and that's really all that matters, right? Is if you inspire confidence, and people are going to believe it. So no, I believe Georgia. Let's identify these variables here, guys. M, of course, is the mass. This is the mass on the end of the spring. And that's going to be in kilograms. And K, of course, is the spring constant. That's just a measurement of how stiff the spring is, as you said in the last equation. That's going to be measured in newtons per meter. And T, of course, is the period. That's the time for one complete cycle. For one complete cycle of this spring going back and forth, back and forth. We've got 2 examples for you. What I'm going to do is give you one example. It's pretty straightforward, relatively straightforward. Give you a little bit of chance to work, and then in 15, 20 minutes, we'll do another example. Give you a little bit more time to work, and then that'll be it. 2 examples and some time to work today. Sorry, before I give you that example, I do want to give you one more little equation, but it's not a new one. If we know the period, we can find the frequency. What is it? It's what? Yeah, we'd say cycles per time as opposed to revolutions because it's not the same context, but it is cycles per time, yeah. But if we have the period and we just calculate it this way, why don't we just say 1 over the period? Now, the first example we're going to do is involving the Hooke's law equation, F is equal to K times X. The second example that we're going to do in a little while is this period equation, or the frequency equation. Yep. Okay, here's the first example, guys. A mass of 12 kilograms hangs from a vertical spring that has a spring constant of 10 newtons per meter. How far will the spring stretch? Now, before I even start this question, let me tell you the answer we get is not going to be a very realistic answer here. This spring constant of 10 newtons per meter, it's a pretty small value. You're going to do a lab next week and to find the spring constant of the spring, and the value that you get will be in that range of 10 to 20 newtons per meter. You're going to find that that's a pretty loose spring. If you put a 12 kilogram mass on the end of that, it's going to stretch it a lot. So the answer isn't necessarily so realistic here, but at least the process works for us here. We've got a spring constant of 10, we've got a mass of 12.0 kilograms, and we're looking for the value of x, the displacement, how far does it stretch? Let's say F is equal to K times X. Why did I say positive KX? Not that it really matters for you, because I told you I'd mark it right either way. we don't know how much the spring is pulling back. We're going to find how much that we're pulling on the spring. So it's an applied force here rather than a restoring force. X is equal to F over K. K is 10 newtons per meter. Good. Oh, wait. I don't know what force is. Anybody? Anybody? What's the force that's acting on this spring? If this 12 kilogram mass hangs vertically from this spring, what's the force that acts? Yep.
Mass times acceleration.
Yeah, we're going to say m times g. So the force here is 12 kilograms times 9.81 meters per second squared. Which is 117.72. So if I pull on this spring, or gravity pulls on this spring with a force of 117 newtons, and that's what it is because it's hanging vertically, we divide that by the spring constant, and I end up getting to 2 digits, 12 meters. Wow, that's a long spring that I just stretched 12 meters. I told you it wasn't going to be a realistic answer. But the process is still good. What I would like you to do now for the next 10 minutes or so, 10, 15 minutes, is take a look at worksheet number 27. Right now, I only want you to look at 1 to 3. After you've done those, we'll do another example, and then we'll let you work on a couple more questions after that, and then that'll be the day for us. All right, now that you've had a chance to work on questions 1 to 3, let's do one more example and then let you work on the next few questions. We'll shut it down for the day after that. Example number 2, this relates to the period/frequency of the vibrating spring, how long it takes to go back and forth. It says the period of a spring's motion is 1 second. So I'm going to say big T is 1.0 seconds. That's big T, not little t, right? Little t is any time. Big T is the time for one cycle. There's a mass of 2 kilograms. A mass of 2 kilograms here, it's attached to the end of the spring. What's the spring constant? Well, we're allowed to try F is equal to Kx here. There's no reason why we can't. But I don't see that as being very useful because I don't know what the force is. I guess I got a mass, but it's not a vertical hanging, so we can't just say it's m times g. I don't think we can do this. It's valid, but it's not helpful. So let's go to my other equation. T is equal to 2 pi square root m over k. Oh, that's a problem. That is a problem because I'm solving for k right there. Ooh. I'm not excited about the algebra in this one. What do you want to get rid of first here? Nope. Not get rid of the root first. Nope. Anybody else? 2 pi. Let's get rid of the 2 pi first. So let's do that by dividing. T over 2 pi equals root m over k. Now, what do you want to get rid of? The root. Yeah, and we're going to do that by squaring it, right? Square root squared. So T over 2 pi squared equals m over k. We're getting there. We're getting there. K's on the bottom, but we want to get it to the top. We're going to take k up to the top by multiplying, yep. So it becomes k times t over 2 pi squared equals m. We're getting there. Want to solve for k? This is one whole term that's multiplied by k. How do you take that one whole term over to the other side? Multiplied by k, take it over by divide. K equals m over t over 2 pi squared. Does that make sense what we did there? Now we got to sub numbers in, right? This is a little tricky even substitution-wise. M is 2 kilograms. T is 1 second, I think, wasn't it? Yep. Over 2 pi. All right, let's, you could, if you're good with brackets on your calculator, go ahead and try that with brackets, but I'm going to recommend a different way this time, because that gets a little ugly with brackets here, okay? I'm going to say, look, just start at the bottom. Like, always start at the bottom, if you're doing it one step at a time. 2 times pi equals, okay, 6.28. Look, I've got that number now, 6.28. Now let's say 1 over 6.28 equals 0.159. All right, I've got this number now. Now let's square that. All right, now I've got this number, the entire bottom. Now let's say 2 over that. 2 divided by that number gives me 78.9. Now I've got this number. How many digits is that supposed to be rounded to? 2 digits. 78.9 will be 79 newtons per meter. Does it make sense what I did there? Got it?
Alternatively, instead of like multiplying the k and then dividing by the all that, could you just like flip both of them around the other way? So it would be 2 pi over t squared equals k over m and multiplied by that.
Yep. Yeah, you could. I hesitate to teach a way like that because, I mean, that's creative, like creative thought, and I like that. But the reason that I showed you to rearrange it the way that I showed you is because it follows those rules that we don't have to kind of step outside of. So does what you did, but you're kind of thinking like a little bit more abstract, which is, there's nothing wrong with that, and it's correct, it'll work. But I'm just not going to teach that way. It's like,
is it okay if we square everything first?
Yep, absolutely. So a couple ways of doing it, right? Okay, you square everything first. You're going to get t squared is equal to 4 times pi squared times m over k, right? And then take the k up, and like different ways of doing it, right? This is just one way that works. All right, let's give a look at not the rest of that worksheet. I only want you to do up to number 7. Up to number 7 on worksheet number 27. For tomorrow, I'll throw the answers up on the board for you. 0.28 seconds, 3.6,